What we're going to look at next is modifying series using series that we already know. So for example, let's say we were asked to find the Maclaurin series for cosine 2x. Everything we're going to be doing is going to be about c equals 0 or this method won't work. Well, again, the normal way you would do it is you would find a bunch of derivatives, plug in 0, hopefully look for a pattern. However, what we can actually do is remember that cosine has the following form, 1 minus, and then it's just the even powers. Okay, plus something squared over 2 factorial, plus something to the 4th over 4 factorial, minus, etc. In sigma form, it's sigma n equals 0 to infinity, negative 1 to the n, something to the 2n, all over 2n factorial. Well, the natural thing to do would be wherever you see an x from before, you just plug in a 2x, and that's exactly what we're going to do in this particular situation. So the power series for this, for cosine of 2x, works out to be sigma n equals 0 to infinity, negative 1 to the n. Notice there's a 2 to the n, and then an x to the 2n, all over 2n factorial. This 2 to the n part is actually what takes care of the chain rule if you were to do this the long way using the formula, because every time you take the derivative, an additional 2 is going to pop out. Okay, let's take a look at a similar example. Let's say we were asked to find the power series for cosine of square root of x about x equals 0. So again, we recognize that cosine just looks like 1 minus something squared over 2 factorial plus something to the 4th over 4 factorial minus, etc. And then you have the sigma form of this, which is just going to be sigma n equals 0 to infinity, negative 1 to the n, something to the 2n power, all over 2n factorial. Well, like before, what we're going to do is we're just going to plug in square root of x, which is really the same thing as plugging in x to the half wherever we used to have an x. Okay, so if we write out the series form, for now you should get 1 minus x over 2 factorial plus x squared over 4 factorial minus dot dot dot. And here it is, sigma n equals 0 to infinity, negative 1 to the n, x to the n, all over 2n factorial. And that is our power series for cosine of square root of x. We can take this a step further, because if we were asked, for example, to find the power series for something like x times cosine square root of x. Now think about this. If you did this a long way, you would find all these derivatives, which would include product rules and then chain rules for the square root of x, and it would just become a mess. So how do we deal with this? Well, from example 9, we know the power series for cosine of square root of x is just sigma n equals 0 to infinity, negative 1 to the n, x to the n, all over 2n factorial. All we're really doing is we're just multiplying through an x. Okay, well, what does that do up here? If we did the same thing from the previous example, that's like taking the series and distributing an x through it. So if we look here at the bottom, multiplying by x is just going to add 1 to all the powers of x. Okay, so similarly, if we bring this in, all that's going to do is add 1 to the power of x. So the final answer in sigma form is sigma n equals 0 to infinity, negative 1 to the n, x to the n plus another x, so n plus 1, all over 2n factorial is your power series for x times cosine of square root of x, which again would have been very complicated if we did it the long way. Now we can take this even further if we're asked to integrate x cosine square root of x dx. Now this problem is actually very difficult. You would have to use integration by parts, and you can see from Wolfram Alpha that it's a very complex solution. However, I know the power series for this. It's what we just did in example 10, sigma n equals 0 to infinity, negative 1 to the n, x to the n plus 1, all over 2n factorial. So all I need to do this problem is to integrate that. And when you're integrating a polynomial, the only thing that really gets affected is the power of x. So everything with an n remains a constant, so I have a negative 1 to the n. The new power, it used to be n plus 1. We just add 1 to the power, so it's now n plus 2 over n plus 2, and then the original 2n factorial plus c. So there's your integral in power series form, which is a lot easier to do than if you did it using integration by parts. Keep in mind that the power series is the same as the function within the interval of convergence, but it doesn't mean that this is the integral of x cosine square root of x. It's the power series representation of its integral. If you look at your chart, one of the ones we have not filled in yet is arctan of x. So how are we going to find the power series for arctan of x? Again, I don't want to take a bunch of derivatives, but I want to take something I know and just modify it from there. So if you think about it, arctan of x, its derivative is 1 over 1 plus x squared. So if you integrate 1 over 1 plus x squared, then that'll give you the power series for arctan of x. If you look back at one of the previous examples, I believe it's example 3 from part 1 of the podcast, we saw that the power series for 1 over 1 plus x squared is negative 1 to the n, x to the 2n. And all we're doing to get the power series for arctan is we're integrating that. So the power series for arctan, it turns out, is going to be sigma n equals 0 to infinity, negative 1 to the n, x to the, it used to be 2n, but now it's 2n plus 1, all over 2n plus 1. Okay, and you can kind of write it out and get a sense of what it looks like. Essentially it looks like this, x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot dot dot. And that gives us an indication that arctangent is in fact an odd function. The last example we're going to look at is an integral that trips up a lot of students, and it's simply this, integral of e to the x squared dx. Many students will try u substitution and come up with some pretty interesting integrals, but it turns out that this is not integrable by the methods we have. In fact, if you test that on Wolfram alpha, you'll get a very surprising result. So what we'll do instead is we'll integrate its power series. If you remember from the notes that e is just the following, 1 plus something squared over 2 factorial plus something cubed over 3 factorial plus dot dot dot. And in sigma form, this just works out to be sigma n equals 0 to infinity something to the n over n factorial. So naturally what we're going to plug in is we're going to plug in x squared wherever we see an x from before. And all we're going to do is integrate that power series. So what we're integrating is sigma n equals 0 to infinity x to the 2n over n factorial dx. So this works out to be sigma n equals 0 to infinity x to the 2n plus 1 all over 2n plus 1 times n factorial plus c, but we tend to leave that out for practical purposes. And you can check that as you write out the series, it would be the same as if we took the series above and integrated term by term.